algorithms paper. The section 1 will be dealing with insertion sort. So I'm going to start with the definition, a bit of an introduction to sorting algorithm. A sorting algorithm is an algorithm that is a bunch of instructions, to be simply speaking, that arranges a given set of elements in a certain order. Generally speaking, if the elements are numbers, then the order is either ascending or descending, which means we are given a collection of numbers. I mean, we'll be putting them either in ascending order or descending order. But let's say we are given some strings, let's say some names, then a sorting algorithm can also be used to put those strings or names in alphabetical order. That's essentially what a sorting algorithm is. A bunch of instructions, a bunch of well-defined instructions to put a given set of elements in a specific order. Let's move on to insertion sort. For a moment, or imagine that we are given an array of numbers, because programmatically speaking, that's how the data is generally presented, in the form of an object in an array. Let's say we are given a bunch of numbers in an array. So how insertion sorting will sort the array or the values in the array is this. In insertion sorting, one part of the array is used to store the sorted values, whereas other part holds the unsorted values. And what we do next, I'm just saying it theoretically, I will show it how it is working. We pick elements one by one from the unsorted part and place each of them in the right position in the sorted part. I have written something in the note. Well, for the moment, ignore that. I'll come to that in a minute. Let's say consider this example where we have these collections of numbers 6, 5, 3, 1, 8. Now to begin with, we can say that this 6, the element at index 0, is the sorted part of the array. So we don't do anything here. We start from 5, we compare, and 5, 3, 1, 8 is actually, this is the unsorted part of the array. And this is, the highlighted part is the unsorted, and this is the sorted. We pick the first element from the unsorted part, which is the element at index 1. We compare it with the elements in the sorted part. And since, let's say we are doing it in ascending order, since 5 is less than 6, what will happen is 5 will go here and 6 will come here. Now we have this part is the sorted part of the array, and this is the unsorted. Now we pick the next element from the unsorted, that is 3, and we will compare it with each element in the sorted. Now 3 is less than 6, 3 is also less than 5. What will happen? I'll put 3 in position 1, and everything else will be moved. I'm writing it like this because this is what happens. I'm swapping their positions. And similarly, we go on. Now, my sorted part is, the values in the sorted part is increasing, and the unsorted part, it is decreasing. Similarly, I compare 1 and 8. This is the basis, this is the core of insertion sorting. Now let me show you an animation that will make it much more clear. Let me refresh it. These are the numbers. See, I'm starting from 6. Now 5 is compared with 6. It's moved in front. Now I go for 3. 3 is first of all less than 6, less than 5. So it again goes to the first one. 1 is less than all three of them. 1 by 1. This 1 by 1 is being shown, which means I am comparing it with each of the elements on the left. Same thing again. 7. But 6 is less than 7, so we just stop there. Again 2, 7, 6, 5, 3, and we put it here. And the last one, 4 is less than 8, less than 7, less than 6, less than 5, and voila. That is what I just showed, and that is how the animation is making it clear. Okay, now how do we implement it in code in JavaScript? How do we do that? So let's go to our code base. First things first. So this is a simple code implementation for the insertion sort. I will be taking some input from the user. So those things are just for demonstration purposes. Main thing is this function, insertion sort. What I am doing at first, this function will take the given array as input, the array of elements. I have taken a functional approach. I can write this both the loops outside too. That doesn't matter, but will take the array as input. Now here we have nested for loops. Let's just focus on the outer loop. What the outer loop is doing, first of all, it is, as I said, I equals to 1. Actually, I forgot to mention that. Let me go back there again. Since we are starting the actual comparison, actual sortings begins from index 1, the element at index 1, it is directly sometimes said that the algorithm always begins from index 1. Because as I mentioned, that to begin with, the element at index 0 is considered or can be easily considered to be the sorted part of the array because it is just one element. And then from index 1 we start the comparison with the adjacent elements on the left. The same thing has been implemented in the code. I am starting from I equals to 1 and traversing through the entire array. That is what this condition is doing. arr.length, which means I will keep on increasing until it reach the last index of the array. Now once in every iteration, let's say we are talking about I equals to 1. The first thing that I do, I create a copy of the element at the first position, because the comparison that we are doing, that needs the value needs to be there continuously for me to compare it with every element. That's how I will be able to shift the position. This is where my nested loops, my inner loop comes into picture. So now what I'm doing, in this inner loop will begin at I minus 1, which means if I is equals to 1, j will be 0. If I equals to 2, j will go from 1 to 0. I am just trying to replicate what I just showed, that whenever, let me go back again, whenever we pick an element from the unsorted part, let's say 1, we compare it with, let's say this is 1, 2, 3, 4. So this is I equals to 3. So I equals to 3, then j will be 2, 1, 0. and I will compare that temp value like that. I will compare the temp value with each of these numbers and I will keep shifting that. That is what I'm doing here. Let's go back there again. I'm checking first that if temp is less than the current value of j, the element just before the current index. Now, if it is less than that, then what I do, I swap their places. I swap their places, and which means, let's go back there again. So if I, which is 1, j, which is at the moment the value at j is 6, and since 1 is less than 6, what I do, I swap their positions. 1 goes here and 6 comes here. That is the meaning of this line, that ARR j plus 1 equals to ARR j. That is how this thing is working. The swapping that I showed you, the, the value that is just next to that j, I put the element, this ARR j, the temp value there, and the temp value's position is changed at j. That shifting that I showed is being replicated in these two lines. In the other case, if the temp is not less than ARRJ, it just breaks the loop and I continue to my next element in the unsorted part. This is how the entire step by step, the thing that I showed you is replicated in code. Now let me go to the terminal and see how it is working. Let me zoom in a bit. Okay, if I do that, it will ask me for some inputs. Let's give it that. 6, 5, 3, 1. Let's throw in our negative number. Also put in 0. Let's see what happens. And as you can see, -8, 0, 1, 3, 5, 6. Our comparisons are working flawlessly. So this is essentially the code implementation of insertion sort. Now I need to show you, or I would like to show you, how this algorithm can be applied to a data set, a huge data set. So let's come back from here. Let's go to our code. So I have actually some data set that has 100,000 randomly distributed numbers. I'm using the same logic that I showed earlier, and I will use this logic to sort this sample data set. Now, in order to know how much time or what's the performance considerations here, I will use console.time that will tell me how much time actually this whole program takes, from reading to writing and everything. So I will first of all go here, my program, wherever it is starting. Let's take console.time, call it clock, and once the program ends, I'll put console.time end clock. Now let's go to the terminal back, and if I run this, let's see how much time it is taking. See, it is hanging, it's not happening just immediately, but let's see how much time it takes. It's still sorting, it's still working. By using console.time and console.timeend, what the advantage is, we will get a sense of the time taken for the algorithm to sort this sample data set. Even though it's not completely accurate, but it still gives a very good idea of the efficiency of the algorithm when it comes to huge data sets, let's say 100,000 or 1 million. It's still sorting. Let's see. I'm sorry for that. I actually compiled a different program. Let's do Node 3. It was Node 1. I'm sorry for that. Now it should work. See, it is saying data sorted successfully and it took 6.4 seconds. Let's try it again. Let's see how much time it takes. 6.362, apparently the same. Let's check what happened in our code base. So this was my original data set. Let me format it. As you can see, the entire thing is random. But if we go to my sorted thing, the whole thing, it is visible that it has been sorted properly. Now, so what we saw here is that even though the data is being sorted, 6 seconds of worth of time it is taking to sort 100,000 numbers. Why is that the case? Well, that's the case because of this shifting. We are comparing the temp value, let's say, or the element in the unsorted part with each of the elements in the sorted part. So as the number of elements increase, we keep comparing and shifting. That shifting and continuous comparison, that is very costly. And that cost is being shown because 6 seconds is a lot of time. So that is it for the insertion sort. We will be moving on to radix sorting after this. That is the section 2 of the video. This is section 2 of the video. This video pertains to radix sorting. Okay, so I'm going to be starting with the purpose, though. Why do we need another algorithm? We already have insertion and many other algorithms. Why radix sorting? So the primary purpose of radix sorting is to provide a non-comparative solution for sorting. As I showed you in the last section, that the entire concept or the entire algorithm or the insertion sort is based on comparisons. We compare elements depending on whether it's greater or smaller. We shift or do not shift the position, but comparison is at the core of the algorithm. But radix sorting is designed in a way that it doesn't require any of those comparison operations or comparison functions. So how, in a nutshell, how does radix sorting achieves that? I'll show an example in a minute, but theoretically speaking, how does radix sorting achieves the goal without comparison? The achievement is done by putting the numbers into so-called radix buckets, which are essentially containers or a set as per their individual digits starting from the ones position. So if we are, let's say, given a digit 876, a number called 876, we start from the rightmost digit in the number, that is the ones place. Here we see it is 6. Now we are not going to do any comparison. Since it is 6, we'll just put it in something called the radix 6 bucket. Now what is this bucket? I have prepared a PDF for that. Let's go there. Suppose this is the data set, the part in the yellow. This is the data set. Now, what's the goal? I want to sort it in ascending order. Let's leave all those things aside. First things first, what we will do is we'll write down, or we'll create our buckets, empty buckets. What are these buckets? As you can see here, we are essentially writing these digits, all the digits in the decimal number system from 0 to 9. Now, what we are doing here is these are all labels for a container, like, or a bucket, the word that is being used. For 2, we call it the radix 2 bucket. For 3, we call it the radix 3 bucket. Similarly, for 9, we will call it the radix 9 bucket. What it essentially means, which will be clear as I move on step by step. First thing first, as I've written here, we check the rightmost digit of every number and place each number in the radix bucket. How? Let's see. First number is 1556. We are starting from the rightmost digit, which means the ones place. It is 6. Since it is 6, we'll put the number 1556 in the radix 6 bucket. There is no comparison here. We are just looking at the digit, and we are looking at the digit at the particular position. For now, it is ones. We'll move one by one to the left. Right now, it is 6. We'll put that in this container, in this bucket of 6. Now, in the 4, ones place is 4. I'll put that in the 4th bucket, or the radix 4 bucket. Similarly, 3556 will go into this radix 6. 593 will go into the 3rd. Similarly, we keep arranging it. 7 will 7, 86 will go here, 29 will go to 9. Next, what we have, as we can see, the order of the elements, we write the elements in the new order. How so? We start from the first number in the leftmost bucket, in the smallest radix bucket. In this scenario, it is the 3rd radix bucket, or the radix 3 bucket has the first number 593. We start from 593, then we go to 4, then 1556. We move down in that order. 3556, 86, then we move on to 7, and then 29. So we write this in the new order. We again create empty radix buckets, all those 10 buckets, and now we'll go to the second rightmost digit, which is essentially the tens place. What if the number doesn't has a tens place, doesn't really explicitly a digit is mentioned there? We'll consider it to be 0. So 593, my tens place is 9, so I just put it in the 9th bucket. So this is how the entire bucket concept is coming in. I just keep looking at the digits of whatever position we are looking. For a particular position, we look at digits in the given number, and we match that particular digit with the radix bucket, and we put that in the bucket. As I said, 4 doesn't have a tens place, it goes in the 0th. Similarly, 7 is there too. 1556, 3556 both have 5 in their tens place, so both of them are in the 5th bucket. Not 5th bucket, radix 5 bucket. and 86 will go to my radix 8, and 7, well, as I said, I again write the elements in the new order. As you can see, it is already coming into order. This thing is already coming in order. Now 4 and 7, this thing has been sorted. 29 is also sorted. 4, 7, 29 has been already done. Now I move on to my hundredths place. Now the question arises, how long we keep continuing it? So these repetition will keep on happening. The same thing happens as I move to hundredths place. We'll look at the digits. If there is no digit, we consider it as 0. If there is a digit, we just look at the digit and put it in the proper bucket. So 4, 7, 29, they're all in the same 0th bucket because they don't have a hundredths place. And what it essentially is doing, we are not modifying the already sorted part. This is the beauty of this algorithm. Even as we keep continuing, whatever has been sorted, it is like actually has been sorted completely. It won't be disturbed at all. 1556, it has a hundredths place. 3556 also, both of them go into the radix 5. 86 doesn't have them. It again goes to the 0th. So again, as you can see in the new order, up till 86, everything is sorted. Similarly, last one, 593 will go to my radix 5 bucket. So as I was saying, it will keep on continuing. How many times I need to repeat this will depend on the largest number of digits in a number. All the numbers in my given collection, whichever number has the most number of digits, that many times I have to continue this step. In the given collection, I had 4. The maximum number of digits in a number was 4, which means I have to repeat this whole bucket process 4 times. As you can see, in the 4th time, we'll be comparing, not comparing, there is no comparison, remember. We will be looking at the digits in the thousands place. That is this 1, 3, and everything else will be automatically coming to the 0th bucket. Whichever element doesn't have a thousands place, it will just be sitting in the 0th bucket. Now 1556 is taken care of. Let's say it's in it not it will come in the radix 1, and 3 will be the radix 3. We just write it in the correct order, and we see, voila, the whole thing has been sorted. Now, how do we implement this whole thing in JavaScript or programmatically? How do we do that? I hope I have been able to make it clear how radix sort achieves the goal of sorting a bunch of elements without any comparison. So let's go to our code base. So we are at our code base. Here, the main function, the main magic is happening in the radix sort function. First things first, what we need to decide is how many times I'm gonna, even though I haven't mentioned anything how we are taking care of the buckets and all, we will be creating buckets. The first thing first that we need to do is how many times that bucket and positions and all will be done. The entire steps that I showed, how many times that I need to done. As I mentioned previously, what I need, the number of repetitions depend on the maximum number of digits in a number in the given collection. So I've written a max digits function that I'm calling with the input array that has been given to me. What I do is a simple thing. I'm using the reduce method on that array for every number, or by the way, for I'm starting the accumulator with an initial value of 1 because maximum digits at least has to be 1. It cannot be less than that. So first of all, what I'm doing for in every iteration, or what reduce does is it calls this function, this callback function, for every number in the array. For every number, what I do, first of all, I convert it into a string and I find the length of the number, which is essentially the digit count in that. Converting it into a string makes it easy for me to count the stuff. So that is essentially the digit count. Now I check using this max function is basically a check if the digit count is less than or greater than the current value of the accumulator. So automatically math.max returns the maximum value among the two. So whatever is the value, I return the accumulator because the returned value for the reduce method need to be carried over to the next call of the callback that which will be caught here. So this is how whichever number has the most amount of digits will be assigned to the ACC, the accumulator, and it will be returned to the iterations, which is a fancy word for the number of repetitions. Now, as you can see, I'm starting the first loop. At the moment, we don't care what's inside. This for loop will work iterations times, which means it will, whatever it is doing to implement the sorting, it will repeat the body that many times, iterations, number of times. Okay, now let's unfold it and let's see what's there. This is how we are creating the buckets. How we are creating the buckets, we are essentially creating a two-dimensional array in which there are 10 empty elements, 10 empty 1D arrays. So let me actually show that here. The array it looks something like this. How would it, and this is actually a very good replica and it will continue up till the 10 empty arrays. 10 empty arrays. What will happen? This is actually essentially a two-dimensional array. Now this empty array has an index 0. We know that. This is 1, this is 2. Since it has 10, so it will actually end at 9. So what we are saying, this empty array will actually act as the radix 0 bucket. This empty will work as the radix 1 bucket. This will be radix 2 bucket, and similarly we'll have up till 3, 4 and up till radix 9. So if we go back, that is exactly what we are doing here. We are instantiating, we are using this array constructor to create an array of 10 empty items. I'm filling it with 0 because it is necessary to call the map method on it. Map is not available for empty arrays. And for every element, I return an empty array. So buckets is essentially the array I showed you. It's a two-dimensional array with 10 empty arrays in it. Now, what I do, I have a nested loop here. So up till now, what I have done is for I equals to 0, what it is doing, it is actually choosing the position. Since I'm repeating it only the number of iterations times, what does it say? For I equals to 0, I mean it is at we are actually at the rightmost, we are looking at the rightmost digit in every number, which means we are looking at the ones place. Now this inner loop will actually traverse through the entire array of numbers that we are given. So the outer loop is taking care of the places that we are looking at. The inner loop is traversing through the entire array for each position. It is simply it is clear from this loop condition that I am starting from 0 and I'm going till n. So I'm starting from the first element going to the last element. What I do is I have written a getDigit function. What getDigit does is that I pass it the number and I give it the place. For the moment, as I said, I is acting as the place, which means I'm looking at the rightmost digit. Ones place, programmatically we can't say ones place, we have to say that we want the rightmost digits. So here a neat trick has been used. First of all, what we do, forget the unary plus for the moment, we convert the number into string, we split it, and we reverse it. What that does is it reverses the 0th element. Let me show it here. Let's say my number was 845. So my 0th position, my 0th digit, the digit at the 0 place, which is the ones place, is 5. So in order to get that, first what I do is okay, let me comment it, otherwise it would throw me an error. From 845 number, I go to the string 845, then I split it into an array, which is something like this: 8, 4, and 5. And then I reverse it. What reversing does, it makes it 5, 4, 8. So now I can just use the place as an index. So now what it does, now what happens, it at index 0, I have the numeric string 5, which is same as the digit I wanted. So I'm just reversing it to get my actual digit. And I'm using this unary plus because, as you can see, it is a string that I get a number. But as I showed you earlier, if let's say this is not available, or it returns me undefined, because it can return me undefined. Let's say since it is 3 numbers and I try to find what is my number at the 4th place. If I do that, what will happen is we start from here 0, 1, 2. There is nothing in 3 or 4th index. So we know that in JavaScript, it will return undefined. That is why this OR operator will kick in. Since undefined is false, it will give 0, and that is what we want. The digit will be considered to be 0. So for that particular I value, I get the digit. And since my buckets are at the moment empty, I use the same digit as an index, and I push the array, the element at that position in the array in that particular bucket. And this flat, what it is doing, it is actually rearranging the elements in the array. As you can see, array, the ARR, the input array, is being reassigned here. This reassignment is putting the elements in the new order. Now here, let's say my digit was 5. And what will happen here is I will access the 5th or the index 5, the radix 5 essentially bucket, the empty array. To begin with, it was empty, it might not be empty in as the iterations go on, and I push that particular element in that bucket, and this loop continues until I traverse through the entire array. Then I again increase the position from I equal to 0, it will go to 1 depending on the iterations, and then this process is continued again. An array is being reassigned again and again, and at the end we should get what we want, the sorted array. So why not? Let's run it. Then we'll be able to see it. Let's go to our terminal. Node 2. I need some elements. Let's take it from what we used earlier. 155639335568927. Let's do that. That was quick. So as you can see, it worked. Now the question is, as I showed in the case of insertion sort, we should be able to apply it. We should be able to apply radix sort on a data set too. We'll use that same 100,000 data set. Let's see what's the performance here. In the last time, if I remember correctly, it was 6.5 seconds. But let's see if the comparison wins or the non-comparison wins. Let's go to our code. Here, I'm using the same code. It's just that the data this time is coming from that data set. I'm using read file sync to synchronously read my JSON data. The data is the same that I showed you earlier. Let me show you again. It has some randomly distributed 100,000 elements. So this time too, we'll use our console.time to get an idea of performance efficiency for this algorithm. So we'll start it there and we'll end it here. We'll end it here. Call it block. All right. So let's run it now. Go to the terminal and let's see how much time it takes. 4. Wow. Last time it took 6 seconds. Look at the difference. Let me try it again. 312 or 334, around 320 milliseconds, not even a total second. 1/3 of a second, it is doing the entire job. So we can think of it here, or this is where the comparison can be done. This is one of the advantages. Since there is no comparison happening in radix sort, we can say that it is much faster. There is no shifting of elements continuously. It is faster than insertion sort. And this is where I can also mention the usefulness of insertion sort. The usefulness comes, so insertion sort will be useful if we have relatively smaller elements. Relatively smaller elements are not smaller elements, smaller data sets, because otherwise that shifting costs us a lot of computation costs. But in radix sort, there are some issues that must be taken care of. First of all, this radix sort is not applicable for floats, obviously, because we don't have any positions available for floats. But there is another problem here. It is not impossible, but it is difficult to sort negative numbers. Let's using radix sort. Suppose I put -86 here. It doesn't make any difference because minus, the algebraic sign, since there is no comparison happening here, never comes into picture. So 86 will still, in my first step, will go into the 6 bucket, and 86, by that I mean, if since it is going to the 6 bucket to begin with, the radix 6 bucket, by the end, it will end up in this place. It will end up here. And that is not the right position. Obviously, it should be at the beginning. If you are doing ascending order, minus 86 should be at the beginning. So the way to do it is to, when we have something like that, we have to extract the elements into the negative elements into a separate array and the positive elements into separate array. In the negative array, we get rid of the sign and then apply the radix sort on it. In the positive array, we apply the radix sort generally. And at the end, we merge them. But before merging, we put the algebraic sign back. And as you can see by my explanation, it is a lot of roundabout stuff is going on. Lot of stuff needs to be done. And this is where a sorting algorithm that uses a comparison function is much more useful. And this actually leads to another disadvantage, the space consumption. In-place sorting algorithm, like in insertion sorting, it is an in-place sorting because in my insertion part, we are not creating any separate arrays. We are actually working with the same array. There is no separate memory being allocated. But in our implementation, as I showed before, we are creating these buckets. It's a two-dimensional array, and in every iteration we are actually working with that extra space, extra memory space. And if, as I said, if you are working with negative integers, we would be creating two more extra arrays. So space consumption is more compared to the insertion sorting. Negative number sorting is a pain in the neck, and it is not applicable for floats. But if we are given that, let's say, as I showed, only if all the numbers are positive, radix sort is really, really fast because there is no comparison. And as I'm showing you the data set that it is being sorted. So that is it for me for the video. Thank you very much for your time. Hope you liked it. Bye-bye.